Somewhere in your brain right now, a neuron is dying.
Not because you are sick, not because something went wrong, just because you haven't used it recently enough for your brain to consider it worth keeping.
Your brain is not a storage device. It is not a library that accumulates everything you've ever learned and holds it safely on a shelf. It is closer to a living ecosystem, constantly pruning what isn't being used, constantly reinforcing what is, constantly making decisions about what deserves to survive. And the single most powerful signal it uses to make those decisions is this. Are you still learning?
The human brain contains approximately 86 billion neurons, each one connected to thousands of others through synaptic connections, bridges of electrochemical signal that form every time you learn something, strengthen every time you use it, and weaken every time you don't. Neuroscientists call this synaptic plasticity, the brain's ability to physically reorganize itself in response to experience, to grow new connections, strengthen existing ones, and prune the ones that have gone quiet. This is not a metaphor. This is a physical process.
When you learn a new skill, your neurons build new physical connections. The myelin sheath surrounding those neural pathways thickens with use, making signals travel faster and more efficiently. The more you practice, the more insulated the pathway becomes, and the more automatic the skill feels. But the reverse is equally true. Stop using a pathway, and the myelin thins. The signal slows, the connection weakens, and if the signal stops entirely for long enough, the connection is eliminated. Not archived, not stored somewhere for later. Gone. This process is called synaptic pruning, and it never stops. Your brain is pruning right now. It pruned while you slept last night. It will prune tomorrow. The question is not whether pruning is happening. The question is whether you are giving your brain enough new material to build with, or whether the net balance is tipping slowly, quietly, irreversibly toward loss. In 2003, neurologist Peter Eriksson at Sahlgrenska University Hospital in Sweden confirmed something that had been theoretically possible but never proven in humans: adult neurogenesis, the birth of new neurons in the adult human brain. For most of the 20th century, the scientific consensus was clear. You were born with all the neurons you would ever have. After a certain point in development, the brain stopped producing new ones. What you had was what you had. Eriksson's research overturned that consensus entirely. Using a chemical marker that incorporated itself into newly dividing cells, his team demonstrated that the human hippocampus, the brain structure central to learning and memory, continues producing new neurons throughout adult life. But here is the finding that changed everything about how we understand mental aging. The rate of neurogenesis is not fixed. It is not a biological constant ticking down at a predetermined pace regardless of what you do. It is directly, measurably influenced by behavior. Physical exercise increases it. Chronic stress suppresses it. Sleep regulates it. And learning, specifically the kind of effortful learning that requires your brain to build new connections, is one of the most powerful stimulants of new neuron production that researchers have ever identified. Your brain does not just respond to learning, it depends on it. In 1994, researchers at the University of California began one of the longest and most ambitious studies of cognitive aging ever conducted, the NUN study. Led by epidemiologist David Snowden, it followed 678 Catholic nuns over several decades, tracking their cognitive health, lifestyle, and eventual neurological decline. When the nuns died, They donated their brains to science. What Snowden found when he examined those brains alongside the detailed records of each nun's life was deeply unsettling. Some nuns showed extensive physical evidence of Alzheimer's disease at autopsy, amyloid plaques, neurofibrillary tangles, the full pathological signature of advanced neurodegeneration. But they had shown almost no symptoms while they were alive. They had remained cognitively sharp, socially engaged, intellectually active, teaching, writing, debating, learning new things well into their 80s and 90s. Their brains were, by every physical measure, severely damaged, but their minds were functioning.
Snowden's conclusion pointed to something neuroscientists now call cognitive reserve. The idea that a brain which has been consistently challenged, forced to learn, adapt, make new connections, builds a kind of structural redundancy, alternative pathways, backup routes, so that when damage occurs, the brain can reroute around it. A brain that has been intellectually active for decades has more pathways to lose before function degrades. A brain that has been allowed to coast has fewer. The damage was the same. The reserve was different. And the reserve was built over a lifetime of learning. But cognitive reserve is not just about old age. It is not something you build at 70 to protect against what might happen at 85. It is being built or not built right now. In the choices you make today about whether to challenge your brain or allow it to settle into comfort. Because comfort for a brain is not neutral. Comfort is a signal. When your brain encounters a situation it already knows how to handle, a routine it has run 100 times, a path it can navigate without effort, it does not engage the same systems as when it encounters something genuinely new. The prefrontal cortex, the region associated with executive function, problem solving, and focused attention, largely stands down. The task gets handed to the more automated systems that handle familiar patterns efficiently. This is efficient. It is also, over time, a form of atrophy. A 2019 study published in the journal Neurology tracked over 2,000 adults across 25 years and found that those who engaged in cognitively stimulating activities, learning new skills, reading challenging material, engaging in complex social interactions, showed significantly slower rates of cognitive decline, regardless of age, education level, or genetic risk factors. The protection was not from doing the same familiar things repeatedly. Doing a crossword puzzle you've been doing for 20 years does not challenge your brain. It exercises a pathway that is already well established. The protection came specifically from novelty, from learning things the brain did not already know how to do. There is a concept in neuroscience called the default mode network, a set of brain regions that activate when you are not focused on a specific task, when you are daydreaming, mind-wandering, or simply existing without directed attention. For a long time, neuroscientists assumed the default mode network was the brain at rest, idling, waiting for something to do. Recent research has revised that understanding significantly. The default mode network is not idle. It is doing something specific. It is consolidating, integrating new information with existing knowledge, making connections between things learned recently and things stored long ago, building the narrative framework that turns isolated facts into understanding. This is why insights often arrive in the shower or on a walk or in the moments just before sleep. The brain was not resting. It was processing, connecting, building. But here is the critical dependency. The default mode network can only consolidate what has been put in. It can only connect new information to existing frameworks if new information is arriving.
If learning has stopped, the consolidation process has nothing to work with. A brain with no new inputs does not enter a stable maintenance mode. It begins reorganizing around what is already there. And what is already there, without reinforcement, begins to fade. In 2012, neuroscientist Eleanor Maguire at University College London published research on London taxi drivers, people who had spent years memorizing the extraordinarily complex layout of one of the most intricate cities on Earth. She found that their hippocampi were measurably larger than average. The region had physically grown in response to the sustained cognitive demand placed on it. But she also found something in the follow-up data that nobody had anticipated. When taxi drivers retired and stopped actively navigating, the hippocampal enlargement began to reverse. The brain, no longer receiving the signal that this capacity was needed, began reassigning the resources. The growth was not permanent. The gain was contingent on continued use. What you build with learning, you maintain with learning. And what you stop building, you lose. So here is what the science is actually saying. Not that you need to become a student again. Not that you need to enroll in courses or memorize facts or chase credentials. The brain does not care about the form learning takes. It cares about effort, about encountering something it does not yet know how to process and being required to build new structure to handle it. A new language, a new instrument, a new skill, a new domain of knowledge that forces existing frameworks to expand and reorganize. The signal the brain needs is simple. This environment is still changing. There is still something here I have not figured out yet. Keep building. Without that signal, the pruning continues. The reserve depletes. The redundancy that would have protected you from the inevitable losses of aging never gets built. You are not a fixed thing that gradually wears out. You are a system that responds to demand. Feed it demand, and it builds. Withdraw the demand, and it consolidates around what remains. Somewhere in your brain right now, a neuron is dying. But somewhere else, if you are doing this right, one is also being born. The question has never been whether the dying stops. It doesn't. The question is whether the building is keeping pace. And that, unlike almost everything else about your biology, is something you still get to decide.